All right, rotation review. First question is, how many rotations does this turntable make per second? So if we're going to do rotations per second, and we have radians per second, since we're already in seconds, we don't have to do too much work. So 4 radians per second. I'm going to put we got 2 pi radians for 1 revolution. So that gets rid of the radians. So we're going to do 4 divided by 2 pi, and we'll be in revolutions per second. And so that comes out to be 0.64 revolutions per second. What's the translational velocity of a point that's 0.4 meters away from the center of the turntable? Translational velocity is the same thing as linear velocity, right? So we're going to take and say, okay, that velocity is going to be r times omega, so 0.4 meters times 4 radians per second, giving me 1.6 meters per second. If the turntable were to experience this angular acceleration, what angular displacement would it cover? Okay, so we start off with initial angular velocity of 4 radians per second. We have a final angular velocity of 12 radians per second. We have an angular acceleration of 2 radians per second squared. And we want to know theta. So we're going to use omega squared equals omega 0 squared plus 2 alpha theta. And so omega squared minus omega 0 squared over 2 alpha is equal to theta. So we put that in, 12 squared minus 4 squared over 2 times 2. And that gives me an angular displacement of 32 radians. That's my angular displacement. Sorry about that. The next set of questions want to know what's a revolution and what's needed to make an object revolve. So a revolution is the movement of an object around another object. We revolve around the sun, and what we need is a force like gravity or tension, friction, or any other number of forces. Normal force would work. A force is needed to keep the object on a circular path. Draw a diagram showing the velocity and the acceleration of a rotating object. So for a rotating object, we have something round. We'll say that something round is spinning this way, and if we look at a point here, the velocity is always going to be tangential to the radius, and the acceleration, the linear acceleration, is going to point in. So what's especially important for the velocity and for the acceleration and for the displacement is that omega is the perpendicular part of the velocity divided by the radius, not any other part, perpendicular part. What is a rotation? Well, in a rotation, an object spins about a point on its axis. It's spinning about itself. We need torque to make that happen. So, linear quantities to angular quantities, we kind of jumped into that a little bit up here. So, theta is going to be position over radius. Omega is going to be velocity over radius. We'll say it's the same radius. How far away we are from the pivot. And alpha is going to be acceleration over the radius, how far away we are from the pivot. For the moment of inertia of an object, moment of inertia, or rotational inertia is what we've been calling it, in general is mr squared. So what affects that are mass, total inertia, and then the distance of that mass from the center. And the general trend here is the farther away our mass goes, the bigger our rotational inertia. All right, number 3, we're applying this force here. And the first part, we're in equilibrium, so we want to know the magnitude of our force. So looking at this, right now in equilibrium, I got mg down, got tension up, my force is in this way. That means I also have a tension down. So what we need to do is go through here and find our torques. So here, the torque would be force times, I believe the outer radius is 0.8. And here, the torque would be tension times 0.2. Now, in the case where we're in equilibrium, since we're at equilibrium, is the special case where nothing is accelerating. In that specific case, the tension is equal to mg, or 50 newtons. So, looking at what we have going on, net torque in this case is going to be equal to 0. And so we're going to have force times 0.8 minus tension times 0.2. So that tells me that force times 0.8 is equal to 50 times 0.2. Nope. 50 times 0.2. And if we solve for the force, that force comes out to be 12.5 newtons. If F were removed, what would the acceleration of the 5 kilogram mass be? Well, if F were removed, my net torque would no longer be 0, it'd be I alpha. And what I'd have is tension times radius. But because we're accelerating now, the net force would be mass times acceleration for the 5 kilogram object, and it'd be mg minus the tension. Now there's the long way of doing this, and you can go look it up, but we're going to stick with the easy way here on the review. The acceleration would be the net force acting on the entire system divided by the total mass of the system. So the net force is just the weight of the object, 50 newtons, divided by 5 kilograms plus I, which is 8, over R, which is 0.2, because that's what the revolution is, squared. So if we do all of that, I gotta jump across the gap here. That means our acceleration is going to be 50 divided by 205 is what it comes out to. So my acceleration comes out to be 0.244 meters per second squared. If you want to see the long way, that's fine, but just note, I am okay for a coupled system, that's this, where we have more than one object, to say that the net force on the system divided by the linear mass plus the rotational mass divided by r squared, that's okay to jump to. I am just fine with that. There's nothing wrong with that. We just have to make sure we identify what's going on. Next one, small washers are moved from the inner part to the outer part. How does this affect the acceleration? All right, so by moving mass out, that's what we're doing. I increases, so it's harder to turn. We add inertia to our system. So we've added inertia to our system. If that's the case, acceleration decreases. Again, if we look at the acceleration as the net external force divided by the mass plus I over r squared, if I make I bigger, I make acceleration smaller. Number 4, we want to know the magnitude of the force F if we're going to be at rest. So here's the deal. The center of mass of the masses of this stick is at 50 centimeters. That's right here. So I have 20 newtons down. Now, for all these forces, I need to go and find the torque. So the torque here is 0. The torque here is 12 newtons times 0.1 meters. So that's 0.12 newtons. The torque here is 12 newtons times 0.3 meters. So the torque is 0.36 Newton meters. Sorry, not 0.36. 3.6 Newton meters. For the 20 Newton object, the torque is going to be 2 Newton meters. And then from this force down here, because it's at an angle, it's going to be the perpendicular part of our force times our radius. So that's F sine 30 times 0.1. So we put all that in, and it's 0.05 F. All right, now if we're at equilibrium, the net torque on this system is 0. And so that gives me 3.6 plus 1.2 minus 2 minus 0.05 F. And if we solve all that for F, it's just math at this point, we get 56 newtons for that force. Now, if we remove force, our net torque is not going to equal 0. It's going to be I alpha. It's going to be 3.6 plus 1.2 minus 2. So alpha is 3.6 minus 1.2 plus 2. Or sorry, 3.6 plus 1.2 minus 2. So 2.8 divided by the rotational inertia, which is 0.4. So alpha comes out to be 7 radians per second squared. So I think what's important on this one is knowing what to do with the perpendicular part of that force. We've got to do force sine theta in order to get that. All right, so we have a wheel, we have its radius, and we have its rotational inertia. If we want the mass is going to be the rotational inertia divided by r squared because it's mr squared. So 1.92 divided by 0.8 squared gives me a mass for this wheel of 3 kilograms. To get the angular acceleration of the wheel, alpha, that's going to be net torque divided by the rotational inertia. Well, there's only one torque acting on this. It's that 28.8 Newton force times the radius of the wheel, 0.8, because it's acting right here on the very edge, divided by 1.92, the rotational inertia. We put that in, we end up with 12 radians per second squared. And then 4 ways that we could decrease the angular acceleration. So, to decrease the angular acceleration, rotational inertia has to go up. So that's either increase the mass of the wheel or increase the radius of the wheel. Or if we wanted to, we could say that the force or the torque has to go down. So if we want the torque to decrease, we could use less force. We could apply the force closer to the axis, or we could apply the force at less than 90 degrees to the radius. So the angular acceleration is net torque over a moment of inertia, or rotational inertia. So we either make the rotational inertia go up or the torque go down. That's what these things accomplish. Jill and the merry-go-round So she's going to stop it in 2 seconds. How much torque does she need? Well, I know that torque is going to be I alpha. I don't have any other information about forces, so we're going to need to go that way with it. I already have the rotational inertia. What I need to get is alpha. So omega 0 is 4 radians per second. Omega final is 0. She's going to stop it. The time to stop it is... All right, so using that, alpha is going to be the change in omega. So omega final minus omega initial over the time. So alpha is going to be 0 minus 4 divided by 2. Alpha comes out to be negative 2 radians per second squared. So my torque is going to be 2 radians per second squared times 500 kilogram meters squared. We put all that in, and my torque comes out to be 1,000 Newton times meters. So, we have a man standing on a platform and rotating. He starts off with a moment of inertia of 500 and he rotates. Is this a closed system? Yes, we have no outside torques. So no matter what happens, what we're going to say is that L initial is equal to L final. Describe what will happen if the man pulls the weights closer to his body and explains why. He's going to spin faster. Again, angular momentum is going to be conserved. He spins faster because as he pulls the weights closer to his body, his rotational inertia goes down, so his angular speed has to go up. So he's actually going to do it. We have that change in angular speed, so L initial is equal to L final. So 500 times pi over 6 rotations per minute. Well, sorry, let's type over, make that seconds. Is equal to I final times, not pi over 6, 6 over pi, 8 over pi rotations per second. So I final, you divide those things out, comes out to be 375 kilogram meters squared, which is what we expect. We want I to go down. All right, number 7, we have a wheel with a radius of 0.8 and a moment of inertia of 50, and it's initially at rest. The axle of the wheel is fixed in place. We're going to shoot a dart at that wheel. So, I'm going to draw the situation here. So we're going to take our dart and shoot it at the edge here. So we're going to rotate about the center. We're going to say L initial is equal to L final. Well, initially all we have is the dart moving. So that's going to be MVA. And then afterwards it's the final moment of inertia times the angular speed. So mv times the radius of the thing equals final moment of inertia of the dart in the wheel. That's mass of the dart times the radius of the wheel squared, plus the rotational inertia of the wheel, plus 50 times omega final. So we can plug all those numbers in. 2 times 20 times 0.8, 2 times 50 times 0.8 is equal to 2 times 0.8 squared plus 50 times omega final. So when you calculate those things out, you get 80 equals 51.3 omega final, and omega final comes out to be 1.6 radians per second. Again, the big idea here is that we're taking initial angular momentum, setting it equal to final angular momentum. Since it's an object moving in a straight line, the initial angular momentum is MVA, and since they hit and stick together, you have to add their moments of inertia together afterwards. All right, number 8, we have a disc at the top of something. The disc is released and allowed to roll. If it rolls without slipping, what's the speed at the bottom and what's its angular speed? We're going to do that over here because I want to draw some graphs. So we have what's going on at the top, and we're going to have what's going on at the bottom. At the top, we could have potential energy, we could have linear kinetic energy, we could have rotational kinetic energy. At the very top, all we're going to have is potential energy because we're at rest at the top. At the bottom, however, because we're rolling without slipping, when we get to the bottom, we're moving, but we're also rotating at the same time. So the words rolling without slipping tell us that linear rotational energy and rotational kinetic energy are happening. Anytime we hear the words rolling without slipping, that's what we have to deal with. So, for this situation, also what's going on is that we have weight, or gravity, turning potential energy into linear translational energy. And then we have friction, turning some of that potential energy into rotational kinetic energy. So, we get mgh, our potential energy, is equal to 1/2 mv squared plus 1/2 I omega squared. And then in order to do this, we need to kind of substitute things here. So it's 1/2 I in this case is 1/2 mr squared. And since we're rolling without slipping, another thing that means is that omega is equal to v over r. So we have v squared over r squared. My r's cross out, and my equation simplifies down to mgh is equal to 1/2 mv squared plus 1/4 mv squared. So my m's cross out, we get gh is equal to 3/4 v squared. And if we solve for that velocity for part A, we end up with 20.6 radians per second. Part B wants to know what's going on if there's no friction. And we'll continue that over here. For no friction, nothing about the top changes. At the top, we still have potential energy. But now at the bottom, because there's no friction, we have all linear energy. So that means really that omega is equal to 0. We're not going to get any spin from this because there's no friction to make that happen. So in this case, mgh is just equal to 1/2 mv squared, and we can plug our numbers in and solve for the final velocity quite easily. I think I solved for something wrong here. Oh, sorry. 20.6 is not the right speed. Why bother me? 10.3 meters per second. 20.6 radians per second is omega. Now, when we come down here and solve for the final velocity without friction, because we don't have any rotational energy at all, we end up going a little bit faster. 12.7 meters per second. And there's no angular speed because we're not turning in any way. How would it change if the disk were replaced by a hoop? By a hoop of the same mass and radius, I would be larger. For a hoop, I is just mr squared. So if I is larger, it takes more work, more energy to spin the object. That means less linear kinetic energy and less speed. So if you were to race the two, the disk would make it down to the bottom first. All right, number 9. What's the potential energy of the rod when it's at the position shown above? When we do potential energy for an object, we are concerned with what its center of mass is doing. We're going to take the average for the whole object. So the potential energy for this object is mgh, and the height there is half the length of the rod. So it's mg times 0.6. So my potential energy is mg times 0.6. We plug those numbers in, and my potential energy is 18 joules. This is a really important thing. Each end of this thing has different potential energy. And by taking the center of mass, what kind of kinetic energy does the rod have at the bottom? It's not moving in a traditional way, so what we're going to say is at the bottom it has rotational kinetic energy. So if I want the angular speed when we're at the bottom and we're completely vertical, all of my potential energy is 0, so everything is rotational. Rotational kinetic energy at this point is going to be 18 joules. So 1/3 I omega squared is equal to 18 joules. I, in this case, is 1/3 ml squared. So omega squared is going to be 18 divided by 1/2 times 1/3 times 3 times 1.2 squared. If you put that in your calculator, you need to have the whole bottom part bracketed. And if you do that, you end up with 5 radians per second. What is the linear speed of the end of the rod? Because that's on a solid moving object, we can find the linear speed of one part of that by saying v is equal to r omega. So that linear speed is going to be 1.2 meters times 5 radians per second. So that final speed comes out to be 6 meters per second.